Hello everyone. Today I am excited to present my project where we build a transformer encoder completely from scratch in PyTorch and construct an interactive Streamlit dashboard to peer inside the model and interpret exactly how it learns. No, rather than treating deep learning models as black boxes or relying on high level libraries like multi-head attention, this project walks through the core mathematical formulations of self attention from first principles. We'll trace the flow of data, see how model stabilizes during the training using learning rate, warm up, and gradient flipping, and then explore this interactive dashboard. As you can see, by entering a custom sentence, we can visualize which token the model focuses on, view different head attentions, map, and also a training telemetry charts. So let's start by walking through some code, PyTorch model code. Let's look at the core architecture. Everything begins with the stated dot product attention function. Here we calculate the raw similarity scores by multiplying the query tensor with the transpose of the key tensors. We scale the squares by dividing by the square root of the high dimensions, which is crucial for stabilizing at gradients. If a mask is present, we replace the mask position with a very simple number like negative 1 billion, so they become 0 after applying the softmax. Finally, we multiply these attention weights by value tensor to get our weighted representations. Here in the multi-head attention module, we define the linear protection layers for query key value and the final mixing projections. In the forward pass, we'll be taking input tensors of shape like batch size, sequence length, and project them. We then reshape and transform them to shape like batch size, num heads, sequence lengths. This splits our representation into a parallel subspaces, letting each head pay attention to different features independently. After attention calculation, we concatenate the heads back together and project them back to the original model dimensions. To inject the sequence order, we implemented both sinusoidal wave encoding and learning parameter embeddings. And learn parameters embeddings both, take the embeddings in the shapes and output compatible tensors of same shape, which are added directly to the token embeddings. Now let's have a look at the training pipeline. It was written in the training.python. To make the model's attention more interpretable, we train the encoder on real sentiment classification dataset. It has the positive and negative sentences. We build a vocabulary class that parses the corpus, maps the words to indices, and prepends the CLS token at index 0 and patch sequence to a length 10 to stabilize our training of our transformer. We then implement two core techniques like a custom learning and a warm-up scheduler. A custom learner rate and warm-up scheduler using a PyTorch lambda LR. The training rate increases linearly for the first 20 steps and then decays. Second, we apply a gradient clipping. So with a maximum norm of 1.0 to prevent the exploding gradients. During each epoch, we compute the Sharon entropy of each attention head to track how focused the distributions are. Logging them to a CSV, we also inspect how attention weights adapt over the training timeline. Now let's explore the live streamlit dashboard, which serves as our explainability portal. In the side, we have can select our layers like either one or two, and attention head index from zero, one like one, two, three as well. So when we give an input sentence, like for example, the film was terrible and boring. There you go. The first panel displays the scale dot product attention heat map. Here we can exact attention coefficients between each pair of words and their axes. The axes are labeled with actual token like CLS. Was like the film was terrible, boring, making it easier to read. And the second panel we display token attribution. Because we are performing classification, the final representation is pulled from CLS token. We approximate the token importance by summing the attention weights flowing into a CLS token across all the layers. We then normalize these scores and use them to highlight the input text. Notice how the words terrible and boring light up in the intense blue, demonstrating that the model is routing its attention to the key sentiment bearing words to make it predictions. Now let's look at the training telemetry. The dashboard loads our logged metrics to plot the attention entropy curves across the epochs. Entropy measures how diffusion attention is. A higher entropy means the head is attending all words uniformly, and the low entropy means it's focusing sharply on a few words. Our training results show three distinct attention had biographies that developed during the training. First, let's keep a layer and head at the values of 1. So the sentiment, so when the layer is 1 and the head is 1, the sentiment detector on the slide, like we have selected layer 1 and head 1 on the slider, we see that it has low entropy profile. It ignores filler words and places a huge portion of its attention but directly on the sentiment. Words like loved or terrible. Layer 1 and head 0. Which is the local tracker. When we switch the layer 1 and head 0, the heat map forms a distinct diagonal pattern. This head is focused on adjacent tokens acting as bigram and trigram parsers that captures the word order. The global aggregator in the second layer, head 2 exhibits a prominent vertical stripes with index 0, the CLS token. This specializes in routing sequence-wide information back to the classification token so that the linear head can read and output a sentiment prediction. To finalize the entire project, like entire application is fully containerized using Docker Compose. The app service builds automatically, maps the port, and excludes a health check that continuously monitors the Streamlit server's responsiveness. This project highlights how building models from first principles helps demystify neural networks. By constructing the attention mechanism manually, logging training telemetry, and visualizing the activations in real time, we can transform a complex black box into a highly interpretable and debuggable systems. Thank you so much for watching.